The brass tube of my old telescope hums faintly as I lift it, its cold metal catching the porch light. I point it skyward, and a thin, bright line appears where Saturn sits, like a ghostly ribbon stretched across night. That ribbon is the planet's rings, a band of ice and rock that has haunted astronomers for 4 centuries. Galileo first saw something odd in 1610. He wrote of handles on the planet, but his lenses were too weak to separate the true shape. He could only guess that something was attached, like a thin veil over a face. I picture his candle-lit study, the scratch of quill on parchment, and his puzzled stare at a blurry disk. A century later, Christian Huygens, with a better glass, called them the magnificent ring. He measured their width with a ruler of imagination, noting they spanned many times the planet's own size. Huygens' sketch showed a thin line, bright against the dark, and it set the stage for all later work. When the Cassini spacecraft slipped past Saturn in 2004, it brought a new kind of eye. Its cameras recorded the rings in sharp detail, revealing gaps, twists, and countless tiny moons hidden within. I find it hard to picture a structure so vast yet so thin, like a sheet of paper stretched across a football field if the field were a planet. The rings stretch from about 7,000 kilometers above Saturn's cloud tops to roughly 80,000 kilometers outward. That is a span of nearly 73,000 kilometers, almost the distance from New York to Chicago, yet the whole thing is only about a few hundred meters thick. A single grain of sand could stand upright in the middle of the band and still be covered by ice and dust. To feel the scale, compare Saturn to Earth. Saturn's diameter is about 9 times ours, and its rings lie far beyond the planet's own bulk. If you placed Earth at the center of Saturn's rings, the ring's inner edge would sit well over the Moon's orbit, and the outer edge would reach past the orbit of the International Space Station. The visual impact of sunlight bouncing off countless icy particles is why the rings shine brighter than the planet itself. Sunlight hits the rings at a shallow angle, scattering off surfaces that range from pure water ice to darker rock. The reflected light creates a silvery glow that can be seen from Earth with a modest backyard telescope. I sometimes stare at that glow, and it feels like a distant campfire, flickering on a cold night, reminding me how light can travel across the void to warm our eyes. Why are Saturn's rings unique? Jupiter, Uranus, and Neptune also have faint, dusty belts, but none match Saturn's brilliance. The rings are composed of particles ranging from tiny grains to house-sized boulders, all orbiting in near-perfect harmony. Their collective surface area is enormous, allowing them to catch and reflect more sunlight than any other planetary system we know. Scientists still argue about the rings' age. Some calculations suggest they are ancient, formed when Saturn's moons were shattered long ago. Others point to the rings' bright, clean ice as evidence of a recent birth, perhaps a comet that broke apart only a few 100 million years back. We don't really know which story is right, and the answer may lie in the subtle color differences across the band. The rings are not a static picture. Gravitational nudges from Saturn's moons carve out gaps, the most famous being the Cassini division, a dark lane about 4,800 kilometers wide. Tiny moons, called shepherds, keep the edges of certain rings sharp, like a fence post holding a field of wheat in place. Their pull creates waves that ripple through the icy sea, a slow, silent music that we can only hear through careful measurement. When I think of the rings, I think of a fragile veil that could disappear in a single cosmic breath. The particles lose energy over time, spiraling inward until they fall onto Saturn's atmosphere, turning into fleeting streaks of vapor. In a few 100 million years, the rings may be gone, leaving only faint traces in the planet's history. Even as the rings fade, they continue to teach us. By studying their composition, we learn about the building blocks of the outer solar system. By watching their motion, we test the laws of gravity in a setting where many bodies interact at once. The rings are a natural laboratory, a place where physics shows its hand in plain view. The rings also spark the imagination of people far from any telescope. Artists paint them as golden halos, poets write verses about their endless circles, and children dream of sliding down a glittering slide that circles a giant planet. That cultural pull is part of why the rings stay in our minds long after the data sheets are filed away. Looking back at the first sketches, the progress is astonishing. From Galileo's vague handles to Huygens' clear line to Cassini's high-resolution mosaics, each step added a layer of understanding. Yet each observer still felt the same awe, the same pull of something larger than themselves. I sometimes sit here, the porch swing creaking under my weight, and wonder what the next observer will see. Will a future probe send back images of rings made of glassy shards, or will the rings have vanished, leaving only a faint halo of dust? The night sky holds its secrets tight, and I can only listen. The rings are a reminder that beauty and science sit side by side. Their sparkle invites curiosity, while their physics demands careful study. In that balance, we find a quiet lesson: that the universe can be both delicate and exact, a place where a thin band of ice can dominate the view of a giant world. As the wind rustles the old pine behind me, a single mote of dust lands on the telescope's lens, blurring a tiny part of the ring's edge. I watch that speck settle, a reminder that even the smallest thing can change a view. The faint smell of cold metal lingers on the probe's sampling cup, a reminder that we are still touching something that never warmed up. I sit here, eyes half closed, listening to the soft hiss of the recorder as it captures the story of Saturn's rings. The first idea that many scientists offered is that the rings are leftovers from the cloud of dust and ice that once swirled around the young planet. Those particles, they say, never coalesced into a moon because the planet's gravity kept them in a thin, flat sheet. It is a tidy picture, like a forgotten quilt left on an attic floor, but the math behind it does not always line up with what the spacecraft have measured. A second proposal comes from a more violent scene. Somewhere in the past, a moon or a comet may have drifted too close to Saturn and been torn apart. The fragments would have spread out, forming a band of debris that settled into the rings we see today. The notion feels right when you picture a fragile ice ball shattering against a hard wall. Yet the size of the shattered body required to make the massive rings we observe is still a matter of debate. I find it hard to picture a single moon large enough, yet not so massive that it would have left a larger scar in Saturn's gravity field. The third theory leans on the concept of tidal forces. Inside a certain distance, known as the Roche limit, a body held together only by its own gravity cannot stay whole. If a comet or icy moon wandered inside that boundary, the planet's pull would stretch it, then rip it apart, scattering its pieces into a flat disk. This idea has the advantage of being grounded in well-tested physics. Still, the exact location of Saturn's Roche limit for icy material is fuzzy, and the ring's current thickness seems thinner than the debris field a fresh disruption would produce. It doesn't quite make sense when you say it aloud. A fresh smash should be messy, but the rings look almost polished. Timescales add another layer of confusion. Some models suggest the rings formed early, within the first few 100 million years after Saturn gathered its mass. In that view, the rings have been aging for billions of years, slowly losing material to Saturn's atmosphere. Other calculations point to a much younger age, perhaps a few 100 million years at most, implying that the rings are a relatively recent feature. The age question matters because it tells us whether we are watching a dying relic or a newborn adornment. The Cassini mission measured the rate at which ring particles drift inward. Those numbers hint at a rapid loss, but they also depend on assumptions about the particle's stickiness, something we cannot yet measure directly. Open questions still hover like moths around a porch light. One puzzle is why the rings are so bright and icy while the surrounding moons are darker and rockier. If the rings came from a moon, why didn't that moon leave behind a trail of darker debris? Another mystery is the existence of gaps and waves within the rings, carved by tiny moons we have only just begun to detect. Those features suggest an ongoing dialogue between the rings and their shepherds, a conversation we have only heard fragments of. I sometimes wonder whether we are missing a whole class of tiny bodies that act like invisible hands, shaping the rings without ever being seen. The evidence for each scenario is a mix of direct observation and indirect inference. Spectra from the rings show a high proportion of water ice, supporting the idea of an icy progenitor. Yet the same spectra reveal traces of silicates and organics, hinting at a more mixed origin. The distribution of particle sizes, many centimeters across, few meters, fits better with a shattered moon than with a slow-settling primordial cloud. Still, laboratory experiments on ice grain collisions show that under certain conditions, particles can stick together and grow, which would favor the leftover disk view. The data do not point cleanly to any single story. When I try to line up the pieces, the picture keeps shifting. The rings may be a hybrid born from both ancient dust and a later smash-up. Or perhaps we are looking at a process that repeats. A moon drifts inward, breaks apart, forms a ring, then the ring material rains down and the cycle starts anew. We do not really know whether such cycles have time to complete before the planet's gravity clears the debris. The idea of a repeating cycle feels poetic, but the physics may not allow it to happen more than once in Saturn's lifetime. Future missions could settle some of these doubts. A probe that dives deep into the rings, measuring particle density and composition at many points, would give us a clearer map of the material's origin. A long-term watch of the rings' brightness could reveal whether they are fading faster than our models predict. Until then, we are left with a set of clues that fit together only when we squint. The rings remain a puzzle, each piece both illuminating and obscuring the whole. The night air on the porch grows colder and the recorder clicks off. I glance at the single, tiny grain of sand that has settled on the wooden rail, its edges worn smooth by countless passes of wind, a quiet reminder that even the smallest fragment can tell a story. The faint hiss of the spectrograph's cooling fans drifts across the porch, a reminder that the rings are not a single smooth band but a patchwork of many parts. I stare at the data screen, eyes tracing the thin lines that betray each component's secret. The 6 main groups, A, B, C, D, E, and F, behave like cousins at a family reunion. A rings are bright, narrow, and dominated by clean ice. B rings carry more dust, their color a dull gray. C rings sit in the middle, a mix of ice and rock. D rings are thick and dark, full of rocky debris. E rings are faint, barely detectable, and made of the tiniest grains. F rings are the outermost, a loose halo of larger chunks. When I first looked at the A rings, the particles seemed almost uniform, like a field of tiny glass beads. In reality, the size spread runs from a few micrometers up to a meter-wide chunk. That range is huge, and it makes the ring's reflectivity change with the angle of the sun. B rings show a different story. Their particles are coated with a thin layer of soot-like material, making them absorb more light. The soot comes from meteoroid impacts that melt and remix the ice, leaving a darker crust. I sometimes wonder how much of that crust is still fresh ice underneath. C rings sit at a crossroads. Some of their grains are pure ice, while others are speckled with silicate rock. The mix gives a patchy look in the telescope, like clouds breaking across a clear sky. Spectra taken in the near-infrared show a faint water ice band next to a broader silicate feature. D rings are the heavy hitters. Their particles range up to several meters, and most are rocky fragments. The density of D rings is high enough that collisions happen often, grinding the rocks into dust. I find it hard to picture how such a chaotic place can stay together for millions of years. E rings are almost ethereal. The particles are mostly micrometer-scale ice crystals, lifted from moons by tiny geysers. Their low mass means they spread thinly, creating a faint glow that is easy to miss unless you stare long enough. The spectrograph catches a sharp water-ice signature with almost no rocky signal. F rings form a loose halo at the outer edge. Here the particles are the largest, some meters across, and they are mostly rock with a thin, icy veneer. The density drops sharply, so collisions are rare and the ring appears as a faint, wispy line in images. The particle size distribution across all rings follows a pattern that scientists call a power law. Small grains are far more numerous than big chunks, but the big ones dominate the mass. In the A rings, the law leans towards smaller grains. In D and F rings, the tail of the distribution stretches further. Ice purity varies dramatically from one ring to the next. In the A rings, the ice is almost as clean as the ice you might find in a deep freezer, few impurities, bright reflection. By the time you reach D rings, the ice is mixed with iron-rich dust, making it look dull and brownish. Spectroscopic signatures give us a map of composition. Water ice absorbs strongly at 1.5 and 2.0 micrometers. Silicates show a broad bump near 1.0 micrometer. Organics leave a shallow slope across the visible range. By comparing these patterns, we can assign each ring its dominant material. Radial density does not stay constant. Near the planet, the A and B rings pack tightly, with mass per unit area comparable to a thin sheet of paper. Moving outward, the density drops in steps, creating gaps where moons have cleared paths. The E ring sits in a low-density valley, while the F ring's density spikes again, though over a very narrow band. I sometimes ask myself whether the gaps are truly empty or just filled with particles too small for our instruments. The answer is probably a bit of both. The Cassini spacecraft saw tiny dust streams that our ground-based telescopes cannot catch. The ring's structure is also shaped by resonances with moons. When a moon's orbital period is a simple fraction of a ring particle's period, the moon tugs repeatedly, carving out a gap or a wave. This process explains the sharp edge of the B ring and the faint ripple in the C ring. Temperature plays a role too. Ice near the planet stays colder, keeping it hard and bright. Farther out, sunlight warms the ice, making it softer and more prone to cracking. Those cracks expose fresh material, altering the spectral signature. I have to admit that we still lack a full picture of how the rings formed. Some theories point to a shattered moon, others to leftover material from the planet's birth. The evidence in the ring's composition hints at both, but the story is not settled. The rings also interact with the planet's magnetic field. Charged dust grains can be lifted or pushed, changing the vertical thickness of the ring layers. In the E ring, this effect is visible as a slight bulge above the plane. When I compare the A and F rings, the contrast is stark. A rings sparkle like polished glass, F rings look like a ragged rope of stones. Yet both obey the same physics of orbital motion, collisional grinding, and radiation pressure. The mixture of ice and rock in each ring determines how it reflects sunlight. Pure ice reflects most light, giving a high albedo. Rock absorbs more, lowering the albedo. Measuring albedo across the rings helps us map the ice to rock ratio. One puzzling feature is the spokes that appear in the B ring. They look like dark lines that drift across the ring, lasting only minutes. Some think they are caused by electrostatic levitation of fine dust, lifted by the planet's magnetic field. The radial variation in density also influences how sound would travel if we could hear it. In denser regions, waves would move faster. In sparse regions, they would slow down. Though we cannot hear them, the physics is the same as in air. If you look at the ring's edge on, you see a thin, bright line that fades into darkness. That line is the sum of all the rings, each contributing its own shade and thickness. The overall profile is a record of billions of tiny collisions. I sometimes wonder whether the rings will survive the next few 100 million years. Models suggest they will spread outward and thin away, eventually disappearing. If that is true, the current view we have is a fleeting glimpse. The composition of each ring also tells a story about the moons that feed them. Enceladus's geysers supply fresh ice to the E-ring, while micrometeoroid bombardment adds dark material to the outer rings. The rings act as a repository for material from many sources. Spectroscopy shows a faint carbon-bearing molecule in the D-ring, likely delivered by cometary impacts. That molecule absorbs a narrow band near 3.4 micrometers, a signature we can only catch with a sensitive instrument. It hints at organic chemistry taking place far from the Sun. In the laboratory, we try to recreate ring particles by freezing water droplets and mixing them with sand. The resulting mixture mimics the spectral features we see, confirming that the rings are indeed a blend of ice and rock. The radial density profile is not smooth. It has bumps and dips that correspond to resonances, moonlets, and clumps. Mapping these features requires precise measurements of brightness and particle count at many points along the rings. When I plot particle size against distance from the planet, a clear trend emerges. Smaller particles dominate the inner rings, while larger fragments become more common outward. This pattern matches expectations from collisional grinding and outward drift. The rings also act as a laboratory for studying how dust behaves in a low-gravity environment. The way particles stick, bounce, or break apart under gentle collisions can inform how planets form from dust clouds. I find it odd that the A-ring, despite being so bright, holds only a fraction of the total mass of the whole system. Most of the mass sits hidden in the denser, darker D and F rings, where we see less light. The spectroscopic data we collect is like a fingerprint for each ring. By comparing the fingerprints to known materials, we can infer the proportion of water, ice, silicates, and organics. This method works even when the rings are too far to resolve directly. One limitation of our observations is that we can only see the side of the rings illuminated by the sun. The night side remains in shadow, hiding possible features. Future missions that can image the rings from multiple angles may fill that gap. The ring's architecture, with its distinct layers and varying compositions, reminds me of a layered cake, each layer flavored differently, each crumb size unique. Yet unlike a cake, the rings are constantly reshaped by forces we are only beginning to grasp. As the night deepens, the faint glow of the rings fades into the dark sky. I watch a single grain of dust drift across the telescope's field, its path a tiny whisper in the vastness. The grain settles, leaving a barely perceptible mark on the sensor. The night air smells of pine and damp earth, and the telescope's metal tube is cold under my palm. I stare at the thin, bright line that circles Saturn, wondering how so many tiny pieces can keep such a steady path. Each speck of ice or rock follows the same rule that guided the moon centuries ago, Kepler's law of orbital motion. It says a body nearer the planet moves faster, farther out moves slower, and the whole set traces an ellipse that is almost a perfect circle here. I picture a single grain, a few millimeters across, caught in that endless glide. It feels like a stone rolling on a smooth, invisible track that never ends. The track isn't smooth, though. Countless collisions nudge each particle, sometimes gently, sometimes with a sharp jolt. When two grains meet, they exchange a tiny bit of momentum, like two billiard balls that barely touch. Those nudges add up. Over millions of years, they cause the rings to spread outward, a process scientists call viscous spreading. Imagine a thick syrup poured onto a flat table. The syrup slowly slides outward, taking its mass with it. The spreading is driven by angular momentum transfer. When an inner particle collides with an outer one, the inner one loses a sliver of speed, the outer one gains a sliver. The inner piece falls a little closer to Saturn, the outer piece climbs a little higher. I try to picture the whole ring as a giant, slow-moving crowd, each member passing a note of speed to the next. It's a picture that feels right, but I admit it's hard to see in my mind's eye. Not all particles act alone. Their own gravity can pull neighbors together, forming clumps called self-gravity wakes. These wakes look like tiny, elongated clouds that stretch along the direction of orbital motion. A wake is not a solid chunk. It is a loose gathering that constantly forms and dissolves. The gravity that holds it together is weak, yet enough to keep the grains in a loose formation for a while. When a wake passes a bright star, the starlight flickers in a pattern that telescopes can record. Those patterns give us clues about the size and density of the clumps. The magnetic field of Saturn adds another layer of complexity. Charged dust grains feel a gentle push from the field, like a feather caught in a soft breeze. The field is strongest near the planet's poles, but even at the rings it can nudge tiny particles. Those grains acquire a tiny electric charge from sunlight and from the plasma that streams through the system. When the charge meets the magnetic field, the grain follows a slight spiral path, drifting a bit inward or outward. The effect is subtle, but over time it can shift the distribution of the smallest particles. I sometimes wonder whether the magnetic push could ever overcome the pull of gravity. The answer seems to be only for the tiniest specks. Larger rocks remain locked in their Keplerian lanes. Moons orbiting just beyond or within the rings act as metronomes, setting up resonances that shape the ring's structure. A resonance occurs when a particle's orbital period is a simple fraction of a moon's period. For example, a particle that orbits twice for every one orbit of a moon feels a regular tug at the same spot each cycle. That repeated tug can clear a gap or pile up material into a bright ringlet. The most famous of these gaps is the one named after the moon that carves it, a dark lane where few particles survive. The moon's gravity sweeps them away, leaving a clean path. Even without a moon, the planet's own rotation can set up resonances. Saturn spins faster than the particle's orbit, and its slight bulge at the equator creates a gentle wobble in the gravitational field. That wobble can line up with particle orbits, nudging them in or out. The result is a faint ripple that spreads across the rings, like a soft echo of the planet's spin. All these forces, gravity, collisions, magnetic push, resonant tugs, interact at once. The rings are never in a perfect static state. They are a restless system that constantly reshapes itself. I sometimes feel the urge to simplify the picture to say the rings are just particles moving around. That would be a mistake. The reality is messier, and that messiness is what makes the rings a living laboratory. Our models try to capture the physics with equations that balance forces and track momentum. They can predict the overall spreading rate, the formation of wakes, and the locations of gaps. Yet the models have limits. They must average over millions of grains, and they cannot follow each grain individually. I find it hard to picture how a single collision fits into a global picture. Observations from spacecraft have helped fill those gaps. When a probe flew through the rings, it measured the density of particles and the speed of tiny electric fields. Those data showed that the magnetic influence is real, but far weaker than the gravitational pull for most grains. The probe also recorded that wakes can be several kilometers long, despite being made of micron-sized dust. Ground-based telescopes add another view. By watching how starlight dims as it passes through the rings, astronomers can map the fine structure of clumps and gaps. Each method, probe, telescope, computer model offers a piece of the puzzle. Put together, they give a picture that is still incomplete but clearer than before. I sometimes think about the age of the rings. If they have been spreading for billions of years, they should have thinned out by now. Some theories suggest they are younger, perhaps formed by a shattered moon. That idea fits the fact that the rings are bright, indicating they have not been darkened by long exposure to meteoroid dust. A younger age would explain the freshness of the material, but we cannot yet say for certain. The evidence points both ways, and the uncertainties are as wide as the rings themselves. What remains certain is that the rings are a dynamic system, held together by a delicate balance of forces. The balance is never perfect, and small changes can lead to noticeable effects over time. When I look up at the thin band of light, I feel a quiet awe mixed with a skeptical curiosity. The picture is beautiful, but it is also a reminder that nature often works in ways that resist simple explanation. The next time a moon passes near a ring edge, I will watch for a faint ripple, a subtle shift in brightness, a whisper of a change that only a patient eye can catch. The rings will keep moving, colliding, clumping, and drifting as they have for ages. Their motion is a slow, steady hum that I can hear in the quiet of the night. I end this thought with the feel of the telescope's cold metal against my fingers, the faint rustle of leaves, and the faint glow of that thin, bright line, a reminder that even the smallest particles can hold a story worth listening to. The thin line of light where the Encke gap meets the bright ring feels like a scar on a stone. I stare at it, wondering why a moon no larger than a city can carve such a clean trench. Prometheus, a rocky body just a few miles across, circles Saturn just inside the bright ring. Its path is a slow, steady beat, tugging on the nearby particles with each pass. Pandora, its partner on the outer edge of the same ring, follows a similar route. Together they act like two hands squeezing a rope, keeping the gap open. The idea that a tiny moon could hold back billions of icy shards seems odd at first. I find it hard to picture a speck of dust holding a wall of sand in place. Yet the math of orbital resonance shows how the moon's gravity nudges particles at precise intervals. When a particle's orbit lines up with the moon's, the pull repeats every few revolutions, either pushing the particle outward or pulling it inward. In the case of the Encke gap, Prometheus repeatedly gives a gentle shove to particles that drift too close. The push adds a tiny amount of speed, enough to move the particle a fraction of a kilometer each orbit. Over many cycles, the particle slides clear of the gap, leaving a dark lane. Pandora does the opposite on the Keeler gap, pulling stray grains back toward the edge. Cassini's cameras caught these motions as faint ripples along the gap walls. The images show bright clumps that appear and fade as the moons sweep by. I recall a frame where a bright knot flared just before Prometheus passed, then dimmed within minutes. Those fleeting flashes are the direct evidence that the moons are doing the work we infer from theory. The gaps themselves tell us about the ring's mass. If the ring were very heavy, a small moon's pull would be too weak to clear a path. The fact that Prometheus maintains a gap only a few hundred kilometers wide means the surrounding material must be relatively light. By measuring the gap width and the moon's speed, scientists can estimate the surface density of the ring particles. That, in turn, hints at the size distribution of the icy grains. Observations also reveal how the particles behave when they collide. Near the gap edges, the particles tend to form narrow streams that follow the moon's orbit. Those streams sometimes merge into larger clumps, suggesting that collisions are gentle enough to let pieces stick together. If the collisions were violent, the clumps would break apart instantly. The quiet nature of the streams points to a low relative speed among the grains, perhaps just a few centimeters per second. One puzzling aspect is why the gaps stay so sharp over millions of years. The ring particles are constantly nudged by Saturn's gravity, by solar radiation, and by tiny impacts from micrometeoroids. All these forces should blur the edges over time. Yet the shepherd moons keep the borders crisp. It seems the resonance effect acts like a constant, invisible hand sweeping stray grains back into place. There are limits to what we can say, though. The exact composition of the particles, whether they are pure ice mixed with dust or coated in a thin frost, remains uncertain. The Cassini spectrometers gave clues, but the data are noisy. We don't really know how the composition changes across the gap, or whether hidden layers of darker material affect the moon's grip. The stability of Saturn's rings may hinge on these tiny moons. If a shepherd moon were to drift away, the gap could fill in and the ring would become smoother. Conversely, a new moon forming within a ring could carve a fresh trench, reshaping the whole system. The delicate balance suggests that rings are not static. They evolve as moons appear, disappear, or shift their orbits. Some models propose that the gaps act like pressure valves, letting excess material escape outward. When a particle gains speed from a moon's push, it may drift into a neighboring ring, where a different moon can catch it. This chain of handoffs could help distribute material across the entire ring system, preventing any one region from becoming too dense. The role of resonance also extends beyond the visible gaps. Tiny wave patterns ripple through the rings far from any moon, hinting that even distant moons can send faint gravitational pulses. Those pulses may help keep the ring thickness uniform, much like a low-frequency hum that steadies a drumhead. In the end, the picture that emerges is one of constant negotiation. The moons press, the particles shift, the gaps breathe. It is a slow, patient process, measured in centuries rather than seconds. I sometimes wonder whether we are watching a snapshot of a system that will look very different a few million years from now. The data from Cassini still hold secrets. New analyses of old images sometimes reveal subtle changes in the gap edges that were missed before. Each re-examination feels like polishing a stone to see a new facet. The more we look, the more we realize how little we truly grasp about the balance of forces at work. Even with all the numbers and models, there is a quiet mystery that remains. Why do some gaps stay narrow while others widen over time? Is there a hidden factor, perhaps a faint, unseen moon or a subtle shift in Saturn's own gravity field, that we have not yet measured? We can only guess, and the guesswork keeps the field alive. As I sit here, the night air cool against my skin, I hear the faint hum of a distant radio transmission from the old spacecraft. It carries a whisper of data, a reminder that our tools are limited but our curiosity is not. The rings keep turning, the moons keep shepherding, and the gaps keep their silent watch. I close my notebook with a soft sigh, noting the last detail I saw. A single speck of reflected light glinting off a grain at the very edge of the Keeler gap, trembling like a tiny firefly caught in a still breeze. The first thing I notice when I stare up at Saturn's rings in the night is the thin, amber haze that clings to Titan like a sigh. It smells, if you could smell it, of cold oil and distant rain, nothing like the dry dust of the moon. That haze is mostly nitrogen, the same gas that fills our own sky but mixed with a heavy dose of methane, the very fuel that powers our lamps. The atmosphere is dense enough that a feather would drift slowly, not tumble. It presses down with a force about 1/3 of Earth's, enough to keep a thin veil of liquid on the surface. Those liquids are not water, they are lakes of liquid methane and ethane, dark patches that spread like spilled ink across the orange-brown plains. When the sun dips low, the lakes glint, reflecting a weak amber light that seems almost too soft to be real. I have read that the surface pressure is about 1.5 bars, but I find it hard to picture a sky that heavy and yet so faint. The clouds that rise there are made of tiny droplets of methane, forming in the upper reaches where temperatures hover near -180 degrees Celsius. They drift lazily, sometimes coalescing into brief storms that rain methane onto the dunes. Those dunes, vast seas of dark, wind-blown particles, are shaped by winds that sweep across the moon at speeds that would barely stir a summer breeze on Earth. The wind's direction changes with the seasons, carving ripples that stretch for hundreds of kilometers. I sometimes wonder if the dunes keep a record of each passing storm, like the rings of Saturn keep a record of each moon's tug. Titan does not orbit alone. It sits in a subtle dance with Saturn's rings. Every 15 orbits, Titan's gravity nudges the particles in the outer edge of the A ring, creating a faint resonance that carves a tiny gap. The effect is barely noticeable, but it shows how even a moon of this size can shape the larger system. It is a reminder that gravity works in quiet, persistent ways, not in sudden bursts. The methane cycle on Titan mirrors Earth's water cycle, but with a twist. Sunlight evaporates methane from the lakes, the vapor climbs, cools, and condenses into clouds. Those clouds fall as rain, refilling the lakes, while some of the rain seeps into the porous ground, forming underground reservoirs. The cycle repeats, driven by a sun that is a distant, dim ember. I sometimes wonder whether the cycle is as stable as we think, or whether hidden heat from the moon's interior throws it off balance now and then. Beneath the surface, the chemistry is even stranger. The methane rain can dissolve simple organic molecules, forming a broth of complex hydrocarbons. Over millions of years, ultraviolet light from the distant sun breaks apart methane, creating a haze of tholins, brown, tar-like substances that settle on the ground. Those tholins are rich in nitrogen and carbon, the basic ingredients for life as we know it. Some scientists argue that, given enough time, such a mixture could spark the first steps toward biology. I admit I'm skeptical about the notion that life could arise in such a cold, dry place. The temperatures are far below the range where water can act as a solvent, and the chemistry proceeds at a glacial pace. Yet the presence of liquid, even if it is methane, shows that chemistry can happen in environments we once thought were barren. It makes me wonder whether we are too narrow in our expectations. Future missions keep pointing back at Titan, as if it holds a secret we cannot ignore. The reason is simple. It is the only moon with a thick atmosphere and stable liquids on its surface. A probe that can land, hop, or even float on the lakes would give us a direct look at the chemistry in action. The idea of a floating drone, skimming the methane seas while sending back data, feels like a scene from an old science fiction reel, but it is being engineered now. There is also the prospect of drilling beneath the dunes to sample the subsurface. If a pocket of liquid water exists deep below, warmed by radioactive decay, it could host a hidden ocean. That ocean would be shielded from the harsh surface, perhaps allowing chemistry to proceed in a more familiar solvent. We do not yet know if such a pocket exists, but the possibility keeps the scientific community awake at night. One of the most compelling arguments for returning is the chance to compare Titan's methane cycle with Earth's water cycle. By measuring evaporation rates, cloud formation, and rain patterns, we could refine our models of planetary atmospheres. Those models help us understand climates on distant worlds, where we only have a faint glimmer of light. The data could also improve our climate predictions here, by showing how a thick atmosphere behaves under a weak sun. The challenges are not small. The distance to Saturn means a round trip takes years, and the cold environment tests every instrument. A lander must survive temperatures that would freeze most batteries solid. The communication delay stretches to over an hour each way, so any mission must be highly autonomous. I sometimes think the engineering hurdles are as daunting as the scientific questions. Still, the allure of Titan remains. Its thick haze hides a landscape that is both alien and oddly familiar. The lakes, dunes, and clouds form a scene that feels like a mirror turned upside down. We have only scratched the surface of what lies beneath that orange veil. Each new image from the Cassini spacecraft added a layer of detail, but also raised fresh questions. When I sit here, the crickets outside my porch are a far cry from the methane rain that falls on Titan. Yet the sound of their chirps reminds me that even in the quiet of night, processes are at work. Whether it is a tiny insect beating its wings or a moon cycling methane through its skies. The universe is full of such quiet motions, and Titan is a prime example. If you look closely at a single droplet of liquid methane on the shore of Kraken Mare, you can see a tiny ripple, a brief echo of the wind that made it. That ripple fades, leaving the surface smooth again as if nothing had happened. It is a small detail, but it holds a whole world of physics in a single moment. The first time I saw the plume, it looked like a thin mist rising from a candle. It was captured by a camera that stared at Enceladus for hours, waiting for a secret to show. The plume emerges from a shallow crater called the Tiger Stripe near the moon's south pole. Its shape reminded me of a breath drawn through a cracked window on a cold night. The stripe itself glows faintly in infrared, as if warmed by an unseen fire. Cassini spectrometers read the plume's light and found water vapor mixed with tiny ice shards. Those shards measured a few microns, like dust that settles on an old bookshelf. The water vapor carries traces of carbon dioxide, methane, and even molecular hydrogen. Each molecule hints at chemistry that could run deep beneath the icy crust. These gases escape at speeds over 1 kilometer per second, racing into space. Scientists think the hydrogen forms when rocky material meets the ocean's water, a process that releases heat. That heat may keep a pocket of liquid water alive under a frozen shell. I find it hard to picture a sea hidden beneath a crust as thick as a winter coat. The idea feels both fragile and stubborn, like ice that cracks but never fully melts. The plume does not spray in all directions. It follows a narrow cone that points outward. When the particles leave, Saturn's gravity catches some, sending them into a faint ring. The cone's angle widens slightly when the moon reaches its orbital high point. This ring, known as the E-ring, spreads far beyond Enceladus's orbit, a delicate halo of ice. Measurements show the ring's density peaks where Enceladus's plume supplies fresh material. The link between plume output and ring brightness is direct, like a faucet filling a bathtub. If the geysers quiet down, the ring would slowly thin, losing its sparkle. Astronomers have measured the ring's brightness drop after a brief plume lull, confirming the link. Observations over several years show the plume's strength varies with Enceladus's orbit around Saturn. When the moon moves closer to the planet, tidal forces stretch its interior, and the geysers flare. Those tides are a slow, relentless squeeze, not a sudden shove. They may crack the ice crust just enough for water to escape. The composition of the ejected ice tells a story about the ocean's chemistry. Salt and silica particles suggest the water has been in contact with rock for a long time. The silica particles appear as tiny glass beads, polished by the ocean's currents. Such contact could provide the energy needed for simple life forms to exist. We cannot say for sure, but the clues are enough to keep us curious. It doesn't quite make sense when you say the ocean might be alive, and yet we have no eyes there. Our instruments can only taste the plume, not see the depths directly. Cassini flew through the plume 3 times, each pass collecting samples like a scientist scooping water from a river. Those samples showed tiny organic molecules, the building blocks of life, scattered among the ice. Each flyby collected thousands of particles, enough to build a statistical picture of the plume. The presence of organics does not prove life, but it does lower the barrier for habitability. In a place where liquid water, heat, and chemistry meet, the odds improve. Future missions aim to return to Enceladus with more sensitive tools. A lander could drill through the crust, reach the ocean, and listen for signs of metabolism. Even a simple probe that measures temperature and pressure could answer many of our lingering questions. We need to know how thick the ice truly is and how stable the ocean remains. Knowing the pressure profile would also tell us how deep the ocean lies. The challenge is that the surface is slick and the gravity is weak, making a landing risky. One slip could send a craft drifting away, lost among the ring's icy particles. Yet engineers are already sketching designs that use the plume itself as a fuel source. By capturing the water vapor, a probe could power a small engine, staying aloft longer. Such a system could keep a probe hovering for months, mapping the plume's variations. Such ideas feel like science fiction, but the data from Cassini makes them plausible. The plume's steady flow provides a natural resource if we learn to harvest it. Meanwhile, the ring continues to echo the moon's activity to distant observers. Telescopes on Earth can track its brightness, offering a remote way to monitor Enceladus. If the ring dims, we might infer a quiet period on the moon without sending a spacecraft. That indirect method could save time and money, though it lacks detail. Remote sensing of the ring's color changes could even hint at chemical shifts within the plume. The habitability question also ties to the moon's age. A younger ocean might be more turbulent, while an older one could be calm and stable. We don't really know how long the ocean has existed, but models suggest millions of years. That span is long enough for simple microbes to adapt, if conditions allow. The icy particles that drift into the ring eventually fall back onto Saturn's atmosphere. There they burn up, leaving a faint trace that our instruments can detect. When the particles vaporize, they release a faint scent of water that our detectors call a signal. This cycle, moon to ring to planet, creates a subtle connection across the system. It reminds me of a quiet conversation between distant friends, heard only in soft echoes. Every new plume measurement adds a grain of sand to our understanding, yet the beach remains vast. We must keep collecting, even if each step feels small. The quiet night on my porch mirrors the silence of Enceladus's frozen plains. Only the faint hiss of a distant plume breaks that stillness. I end my thoughts watching a single ice grain linger in the lamp's warm glow, trembling. The faint glint of a half-meter pebble caught in a telescope's glare reminds me how small some of Saturn's companions truly are. I sit here, porch light flickering, and think of those specks that orbit a giant like dust on a wind-blown pond. The tiny moons fall into families that astronomers have given names to, like the Alkyonids and the Norse. The Alkyonids cluster near the rings, while the Norse wander far out, each group sharing similar orbits and shapes. I cannot help but wonder whether these clusters formed where they sit now, or whether they were snatched up long ago. Capture would mean a wandering rock was pulled into Saturn's grip, while in situ birth suggests they coalesced from ring debris. The evidence for capture lies in the odd inclinations of many Norse moons. They tilt at angles that rings rarely reach. Their eccentric paths feel like scars from a violent grab, but we lack a clear picture of how that could happen without tearing the rings apart. On the other hand, the Alkyonids sit just beyond the ring, moving in near circular lanes. Their smooth orbits hint that they may have grown from the same material that makes the rings, particle by particle, over eons. Surface albedo tells another part of the story. Some moons shine like fresh snow, reflecting most of the sunlight that hits them, while others absorb light, appearing as dark as basalt. Those bright faces often match icy ring particles, suggesting a common makeup. The darker moons, however, look more like carbon-rich asteroids that have spent time in the outer solar system. Their muted tones could be the result of space weathering, or perhaps they are fragments of an older satellite that broke apart. When I stare at the rings through a spectrograph, I see that the tiniest moons sometimes leave faint trails of dust behind them. Those trails are not just decorative, they are the result of constant collisions with ring particles. Each impact knocks loose a grain of ice, which then spreads into a tiny halo around the moon. Over time, that halo can alter the moon's shape, making it look more like a rounded pebble than a jagged rock. The rings themselves feel the pull of these moons, too. A moon's gravity can open a narrow gap in the ring, carving out a lane that persists for millions of years. The famous Keeler Gap is a prime example, kept clear by the tiny moon Daphnis. Even the smallest moons can create wave patterns that ripple through the rings, like a stone dropped into a still pond. Those waves travel outward, changing the density of ring particles and sometimes forming bright spokes that we can see from Earth. What these interactions reveal about ring longevity is both hopeful and sobering. If tiny moons can shepherd ring material for billions of years, perhaps Saturn's rings are more stable than some models predict. Yet the same moons also act as agents of loss, nudging particles into Saturn's atmosphere where they vaporize. Each tiny collision chips away at the ring's mass, a slow erosion that may eventually thin the system. I find it hard to picture the exact balance between shepherding and erosion. The numbers are small, and the processes overlap. Some researchers suggest that the current ring mass could survive for another 100 million years, while others argue it may fade much sooner. The composition differences among the moons give clues about the ring's own makeup. If a moon's surface matches the icy particles of the A ring, it strengthens the case that the moon formed from that ring material. Conversely, a moon with a rocky, dark surface suggests it arrived from elsewhere, perhaps a captured comet that never fully melted. Those outsiders may have delivered foreign material into the ring system, altering its chemistry. Ring particles themselves are not uniform. They range from micrometer-sized grains to chunks as large as a house. When a moon sweeps through, it preferentially gathers the larger pieces, leaving a finer dust cloud behind. That dust cloud can be seen as a faint halo in high-resolution images, a ghostly ring that circles the moon like a breath. The halo's brightness changes with the moon's position, hinting at how often it collides with fresh material. The Norse moons, with their steep inclinations, sometimes plunge through the ring plane, creating brief but dramatic disturbances. Those passages can stir up vertical ripples that rise above the ring's flat surface, a reminder that the system is three-dimensional. I sometimes imagine the rings as a living tapestry, but the word tapestry is off-limits, so think of them as a layered blanket, each layer moving under the pull of countless tiny bodies. The moons are the needles that stitch or tear that blanket, depending on their motion. Observations from the Cassini spacecraft gave us a close look at several of these moons, revealing craters, ridges, and even possible cryovolcanic vents. Those vents, if they exist, could spew fresh ice into the surrounding rings, replenishing material that otherwise would be lost. The presence of craters tells us that impacts still happen, even in this crowded neighborhood. A fresh crater on a tiny moon is a sign that a ring particle, or perhaps a stray meteoroid, struck with enough force to leave a mark. In some cases, the crater's ejecta blankets the moon's surface, darkening it and lowering its albedo. That process can explain why some moons appear darker than their neighbors, despite sharing the same environment. When we compare the ages of different moon families, a pattern emerges. The Alkyonides seem younger, their surfaces less scarred, while the Norse moons bear older, more weathered faces. That may point to a timeline where inner moons formed later, after the rings settled into a more stable state. The idea that rings can spawn moons is not new, but the evidence is still tentative. The process would require enough material to clump together, overcoming the planet's tidal forces that normally pull objects apart. Saturn's gravity creates a region called the Roche limit, inside which a body cannot hold itself together by its own gravity. Yet some moons sit just beyond that limit, where clumping becomes possible. If a moon formed just beyond the Roche limit, it could act as a seed, gathering nearby particles and growing larger over time. The Alkyonides might be such seeds, slowly accreting ring material as they orbit. The Norse moons, however, lie well outside the Roche limit, making in situ birth less likely. Their distant orbits and high inclinations are more consistent with capture, perhaps during a chaotic early period of the solar system. Our models still struggle with the exact mechanisms that could bring a wandering rock into a stable orbit without destroying the rings. Some suggest that gas drag in Saturn's early atmosphere could have slowed the rock enough to be captured. Others propose that a series of resonances, gravitational nudges from larger moons, could have shepherded a stray object into a safe lane. Both ideas have merit, yet we lack direct evidence to favor one over the other. The small moons also serve as timekeepers for the rings, marking changes that happen over geological spans. By tracking their orbits and surface features, we can infer how the rings have shifted and thinned. If a moon's orbit drifts outward, it may be pulling ring material along with it, acting like a tiny conveyor belt. That motion could slowly spread the rings outward, altering their density profile. Alternatively, a moon that spirals inward could be a sign that the rings are losing mass, allowing the moon to fall closer to Saturn under gravity's pull. Both scenarios hint at a dynamic system that is far from static. The fact that we still see these moons today tells us that whatever processes are at work, they are not rapid enough to erase them within a few million years. Their persistence suggests a balance, a slow dance between creation and destruction. I sometimes sit and stare at a single pixel of data, a speck that represents a moon no larger than a house. The quiet of the night makes me aware how small our knowledge is compared to the vastness we study. In the end, the tiny moons are like silent witnesses, holding clues about the rings' past and future. Their surfaces, orbits, and interactions whisper a story that we are still learning to read. A final glance at a faint, icy dot on a photograph reminds me that even the smallest objects can shape the grandest structures. The next time a ring particle brushes past a moon, a tiny ripple will form, unnoticed by most, but forever part of Saturn's hidden world. The first thing I notice when I stare at Saturn's rings through the old spectrograph is the faint hiss of the detector, like a moth's wing against glass. It is a reminder that every photon we catch is a tiny whisper from a place that has been shifting for ages. Scientists have measured the ring's age in two very different ways. One line of work looks at the amount of dark material that has settled on the icy particles. That method gives a number close to 100 million years, just a blink compared with the planet's own history. Another approach counts the amount of mass that the rings still hold and works backward from how fast that mass should be lost. That route points to several billion years, almost as old as the solar system itself. The gap between the two numbers is as wide as the space between the A and B rings, and it makes me pause. I keep a notebook of the ways the rings spread outward. The particles, each no larger than a grain of sand, bounce and nudge each other. Their tiny collisions cause angular momentum to shift, and the whole structure slowly widens. At the same time, some material drifts inward, slipping towards Saturn's clouds of gas and eventually disappearing. The process is not smooth. It is a series of tiny jumps and pauses, like a tired clock that sometimes skips a tick. Mass loss is another piece of the puzzle. Tiny meteoroids, bits of rock no larger than a pinhead, rain down on the rings at a steady pace. When they strike, they vaporize a sliver of ice, turning solid into a thin gas that Saturn's magnetic field sweeps away. Over millions of years, this sputtering chips away at the ring's total weight. I have tried to picture a ring that is losing a few kilograms every second. It feels like watching a sandcastle erode under a gentle tide. Solar radiation also nudges the rings. The sun's light pushes on the icy grains, giving them a tiny push outward. That pressure is minuscule compared with Saturn's gravity, but over billions of years it can add up. The effect is strongest on the smallest particles, which are the most easily tossed about. I find it hard to imagine how a photon's feather-light touch can matter on such a massive scale, yet the models insist it does. Computer simulations have tried to stitch these effects together. One set of runs starts with a massive, dense ring that is a few hundred kilometers thick. The code lets particles collide, spread, and lose mass to meteoroids and radiation. After a few 100 million simulated years, the ring thins. Its outer edge moves farther from Saturn, and a halo of dust forms around the planet. Another set begins with a thin, young ring and watches it dissolve into a faint veil of particles that drift into the planet's upper atmosphere. The two outcomes sit side by side, reminding us that we do not have a single answer. There is also the notion that rings could be reborn. Some researchers suggest that a comet or a shattered moon could dump fresh ice into Saturn's orbit, forming a new ring system. In the simulations, a sudden injection of material creates a bright, compact band that then follows the same spreading and loss patterns as the older rings. The idea sounds hopeful, but the odds of such a collision are low. I sometimes wonder whether we are reading too much into a chance event. The future of Saturn's rings may be a quiet fade. If the current loss rates hold, the rings could lose most of their mass within the next few 100 million years. That would leave behind a faint ring of dust, barely visible even to the most sensitive instruments. In that scenario, the rings we see today would be a brief flash in the planet's long story, a momentary sparkle that will soon dim. Other simulations paint a slightly different picture. They include the pull of Saturn's moons, which can act like shepherds, corralling the particles and slowing the spread. In those runs, the rings persist longer, perhaps for a few billion years, but they still shrink and thin. The moons themselves can be damaged by the rings, shedding material that feeds back into the system. It becomes a tangled web of give and take, and I admit I sometimes lose track of which direction the flow goes. Observations from the Cassini spacecraft have added real-world checks to the models. The spacecraft measured how fast the rings are spreading today, and the number matches the lower end of the simulated rates. It also counted how many micrometeoroids strike the rings each hour, giving a concrete loss figure that the models can use. Yet the data are still noisy. The instruments were designed for many other tasks, and the ring signal is often buried under Saturn's own glow. We don't really know every detail, and that uncertainty keeps the debate alive. One thing that is clear is that the rings are not static. They are a living, breathing structure that responds to every gust of solar wind, every stray rock, and every tug from a moon. Their history is written in the size distribution of the particles, in the color gradients that show where dust has settled, and in the faint ripples that mark past collisions. Reading that history is like trying to read a weathered diary written in a language that changes with each page. When I think about the rings past, I picture a time when they were far denser, perhaps a thick disk of ice and rock that formed after a moon was torn apart. In that age, the rings would have been bright enough to cast shadows on Saturn's clouds. Over time, the same forces that now wear them down would have been at work, slowly turning a solid disk into the airy bands we see now. The picture fits the older age estimates, but it also fits the younger ones if we assume a later breakup event. The present is a snapshot of that slow transformation. The rings are spreading, losing mass, and being reshaped by moons like Enceladus, which sprays water vapor that can stick to ring particles. The balance between loss and replenishment is delicate, and a small shift could tip the system toward rapid dissipation or brief renewal. That balance is what the current generation of models tries to capture, and each new run adds a tiny piece to the puzzle. Looking ahead, I keep an eye on the next set of simulations that include more realistic dust physics. Those models let the smallest grains be blown away by radiation pressure, while larger chunks stay put longer. They also allow for occasional large impacts that could dump fresh ice. The outcomes are varied. Some runs end with a thin, dark halo that lingers for 1 billion years. Others end with a complete disappearance of any visible ring material. The spread of results tells me that the future is not set in stone, but it is also not a wild guess. In the end, the story of Saturn's rings is a tale of loss and occasional gain, of slow spreading and sudden collisions, of sunlight nudging icy grains and meteoroids carving away at them. It is a tale that we can trace only by stitching together observations, lab experiments, and computer runs. We have a good sense of the main threads, but many details remain fuzzy. I sometimes feel the weight of that uncertainty like the cool stone of a porch step under my feet, solid enough to stand on, yet reminding me that I could slip at any moment. As the night deepens, the faint glow of the rings drifts across my mind like a thin veil of frost on a window. I notice a single, bright speck at the edge of the A ring, catching the distant sun, and I let that tiny flash be the last thing I hold onto. The cold metal of an old brass telescope sits in a drawer, its lenses dulled by decades of dust. I lift it, feel the weight of its polished barrel, and think of the first eyes that peered through it at a thin, pale band circling a distant world. I have watched the story of Saturn's rings unfold like a slow-moving picture on a porch swing. It begins in the 17th century, when Christian Huygens first described a thin, flat disk around the planet. He sketched the rings with a steady hand, his lines trembling like the night wind. A few years later, Giovanni Cassini noticed a gap, later named the Cassini division, splitting the rings into bright and dark bands. Those early marks were simple, but they opened a gap in our understanding that would stretch for centuries. The next leap came not from a hand-drawn sketch but from a glass plate. In the 1800s, William Herschel used a larger refractor to record the ring's subtle twists. He noted that the outer edge seemed to wobble, a hint that the rings were not a solid sheet but a swarm of countless particles. Herschel's notes read like a whisper of doubt. "I cannot be sure what I see, yet it feels like a sea of stones." I find it hard to picture a sea of ice and rock swirling around a planet, but the image has stuck with me. Fast forward to the age of rockets. In 1979, the Voyager 2 spacecraft swung past Saturn, sending back images that filled the dark of my attic with bright, crisp bands. Those pictures were the first high-resolution glimpse of the ring's texture. The images showed countless spokes, fleeting shadows that seemed to flicker like fireflies caught in a net. It was as if the rings were breathing, each breath a tiny collision of particles. Then came Cassini, a name that still brings a soft smile to my face. Launched in 1997, it spent 13 years circling Saturn, slipping between its rings like a moth through a lantern's glow. One of its most striking feats was the series of ring-plane crossings. The spacecraft deliberately dove through the thin plane of the rings, allowing its instruments to measure the size and composition of the dust and ice grains directly. Those crossings felt like stepping onto a fragile bridge made of glass beads, each step recorded by sensors that sang back data to Earth. Cassini also turned its camera toward the rings at angles no telescope could achieve. With its narrow-angle camera, it captured the propellers, small disturbances caused by moonlets hidden within the rings. Those propellers look like tiny, warped ripples, evidence that even the smallest bodies can shape the whole. The mission also mapped the thickness of the rings, finding them surprisingly thin, just a few tens of meters deep, like a sheet of paper stretched over a cosmic pond. Technological tricks made these images possible. The camera used charge-coupled devices that could count single photons, turning faint glints into clear pictures. A tiny gyroscope kept the spacecraft steady as it skimmed past icy particles traveling at tens of meters per second. The data stream was compressed, sent across a vacuum that took over an hour to reach Earth, then decoded by engineers who stared at numbers as if they were fingerprints of the rings themselves. Public fascination fed the mission's vigor. When Cassini sent back the first image of a ring spoke, in 2006, news outlets ran the picture on front pages, and children drew the rings on school walls. That buzz helped secure funding for the mission's extended phase, the grand finale, where the craft dove between the planet and its rings before meeting a fiery end. I sometimes wonder whether the public's awe was the real engine that kept the project alive, or whether the scientists' own curiosity was enough. The truth, I suspect, sits somewhere in the middle, like a particle caught in a gentle eddy. Looking ahead, the next steps feel both familiar and new. NASA's Dragonfly mission, though aimed at Titan, carries a suite of instruments that could be repurposed for a future ring explorer. Imagine a small drone that rides on a passing particle, sampling ice, measuring temperature, perhaps even listening to the faint hum of collisions. The idea sounds like a story told by a child, yet the engineering plans are already on the table. There are also proposals for a dedicated ring orbiter. Such a craft would stay in the plane of the rings, using a solar sail to adjust its altitude, hovering just above the icy debris. It could map the rings in 3 dimensions, tracking how a single grain moves over weeks, months, years. The data would help answer why the rings are so bright today, when models suggest they should have faded long ago. Some scientists think a recent comet collision replenished the ice, while others argue that a hidden moon constantly feeds fresh material. I don't have a clear answer. The numbers shift like sand in a glass jar. Even without a new spacecraft, Earth-based telescopes are getting better. Adaptive optics on large mirrors now correct for atmospheric flicker, letting us see the rings as if we were standing on Saturn's surface. The James Webb Space Telescope, though focused on distant galaxies, can also stare at Saturn in infrared, revealing temperature differences across the rings that hint at composition changes. Each new tool adds a layer to the picture, a new brushstroke on a canvas that never quite finishes. The public's role continues to grow. Social media platforms now let anyone watch a ring crossing in real time, with commentary from scientists who explain each dip and spike. Schools organize live viewing parties, where kids watch the ring's shadows dance across a screen while a teacher points out the hidden moons. Those moments turn abstract numbers into something tangible, something you can point to on a screen and say, "That is where the ring ends." I sometimes sit on my porch and stare up at the night, the faint glow of Saturn a pinprick far beyond the trees. I think of the countless hands that have traced its outline, from Huygens ink to Cassini's digital files, and the many more that will one day touch its rings directly. The rings are not just a band of ice. They are a record of our attempts to see, to measure, to understand. Each new observation adds a grain to that record, and each grain reflects a bit of our own restless spirit. The wind rustles the old porch swing, and a moth flutters close to the light. Its wings catch a stray beam, scattering it into tiny sparks that vanish as quickly as a comet's tail. I watch the sparks fade, and for a moment the rings feel less like distant objects and more like a quiet, endless ripple that we have only just begun to hear.